Welcome back. We are going to continue with section 15.2, part B. Uh, Earlier in part A of the concept video, we saw how to integrate double integral over general regions, not necessarily a rectangle. So we saw problems and examples too for that one. Now we are going to see another concept known as reversing the order of integration. Why do we need to reverse the order of integration? Sometimes it may not be possible to keep the order of integration as given in the problem. If we change the order of integration by changing the limits of integration suitably, then evaluating the integral will become easy. Following is the example to show how reversing the order of integration and adjusting the limit suitably makes the integral simpler to evaluate. We'll take this example. Evaluate the iterated integral 0 to 1, integral x to 1, sine of y squared dy dx. So if you look at this integral, you notice the first thing that comes to our mind is that, okay, I have the inner limit, inner integral is with respect to y, then the outer integral is with respect to x. So you notice that one is definite, x limits are definite, 0 to 1, y limits are not. Y limits are from x to 1. So they are not definite limit. Its lower limit is not a number. So first let's see the way we have handled the earlier ones. So can we do the problem the way we did earlier problems? So if we had to do that way, then we have to integrate sine of y square with respect to y. So how do we integrate sine of y square with respect to y? That's not possible. So we cannot integrate as given in the problem. We keep the limits as given in the problem, we cannot integrate. So what do we do? So how do we first write down the domain? So first, sketch the original domain. So if we notice here, the domain is given to be all those xy such that x runs from 0 to 1, x runs from 0 to 1, y runs from x to 1. So the lower limit of y is x, upper limit of y is 1. So this is the original domain. So can we sketch this? So let's sketch this. So we're going to take x-axis, y-axis here, x and y. X is running from 0 through 1. Let's imagine this is 0 and this is 1. Y is running from 0 to x equal to y equal to x to y equal to 1. What is y equal to x? Y equal to x is a straight line passing through the origin. So this is y equal to x. What is y equal to 1? So y equal to 1 is a horizontal line. So y equal to x to y equal to 1. So the region that we are given is this region. And they meet, these two meet at x equal to 1 and y equal to 1, right? So the region of integration given region of integration is this region. This is the domain. Now, if I keep the limits the way it is given in the problem, we already saw that we cannot integrate. So what we have to do in the next step is to reverse, keeping the domain as is, reverse the order of integration. In other words, revise the domain. By revise the domain, I don't mean revise the region of integration, but revise only the limits. So we are going to write revised limits. So D will become all those xy. Now, if we keep the limits of y fixed, limits of x varying, which switch the order, so I want to keep the limits of y fixed. Y should be fixed. So y runs from 0 through 1 here. Y runs from 0 through 1. So if I change the revised limits, y equal to x, y equal to 1, then this is y equal to 0, which is x-axis. So now I'm changing y equal to 0 to 1, but I should be still in this domain, but I have to change the limits for x. Here in this original one, it runs from x to 1. Y runs from x to 1. But I want to make it x running from, I am going to make the varying x. So x here is on the y-axis, so x equal to 0. Because it's already y equal to x. Here I'm going to write instead x equal to y. So I'm going to make the limits for x varying. That way I've not changed the domain though. The domain still remains the same. I'm only changing the limits for the variables. So x runs from 0 to y. So the limits now you change the limits and do the integration. See whether you can integrate now. Previously it was integral 0 to 1 to integral x to 1 sine of y square dy dx. What we have done, we have revised the limits, and then now x runs from 0 to y, 0 to y. The fixed limit should be always outside from 0 to 1 sine of y square, because the inner limit is for x, so you have to integrate with respect to x and then with respect to y. Previously it was dy dx, now it becomes dx dy. What is the advantage? Will we be able to integrate now? Y runs from 0 to 1, just definite limit. Now I have to integrate sine of y square with respect to x. When you integrate with respect to x, y and any function of y is a constant. So sine of y square is a constant, then times x, integral of 1, which is x. You are integrating with respect to x. Now you plug in the limits x equal to 0 to x equal to y. Then you're going to integrate with respect to y. So it is integral y varying from 0 to 1. Now you plug in the limits. So it's y, plug in the limits for x. So sine y sine of y square. Then at the lower limit x equal to 0. Now we can easily integrate by suitable substitution. Use sub method. So use sub method works now. So y square equal to u or du equal to 2y dy. So it is integral sine of u, then you have y dy, that y dy is half of du. Whenever we change the limits, we should also, whenever we change the variable, whenever we make a substitution, we have to also change the limits. The y limits are 0 to 1. Y equal to 0, so u equal to 0. Y equal to 1, u equal to y squared, so which is also 1. So here there is no change in the limits, but be aware that you may have to change the limits, proper lower limit and upper limit whenever you make a u substitution. So it is 1/2 integral of sine u, that is negative cosine of u between 0 and 1. So it is negative 1/2 cosine of 1 minus cosine of 0. That is negative 1/2 cosine of 1. Cosine 0 is 1. Now you can write this as half of 1 minus cosine of 1. So that is the value of the limits, even though we were not able to integrate if we had kept the limits as it was given in the problem, but by reversing the order of integration, we were finally able to integrate. That is integral 0 to 1, integral 0 to 1, integral x to 1, sine of y square dy dx. So order of integration, reversing the order of integration sometimes is very helpful to evaluate certain integrals which we normally think we cannot. Hope this video helps. And also, yeah, there is one more concept we have to cover in this section itself, which is average value of a function. This is kind of an extension of an idea that you did in Calculus 1 class. In Calculus 1 class, what you did was in single variable. So if you have a function defined over the interval a to b, then the average value of the function is defined to be 1 over the length of the interval over which the function is defined, 1 over b minus a, integral a to b, fx dx. So it is single variable, then the function is defined only over the interval. But suppose we assume that the surface is defined over a rectangle, or then f average would be equal to 1 over area of area of the rectangle. Instead of the length of the rectangle, length of the interval in single variable, it becomes area of the rectangle, then double integral over r f of xy dA, where area a of r stands for area of the rectangle r. So all you need to do is to find out the area of the rectangle and divide, and then the usual double integral method you have to do for double integral over r f of xy dA. Then, as I said earlier, you may want to refer to the problems, problem number 7, 21, 25, and all these problems are done, including number 51. All these are reversing the order of integration. There is one more problem for you to refer to in the videos for section 15 too. Please refer to those videos for additional suggested problems. Hope this video helps.